We're getting close to the end. This is the 8th lesson on Taylor series, or I should say power series. Specifically, this one's about Taylor series and approximations. It's kind of an odd one to me because this particular section tends to be challenging for students. It's really easy to get lost in um, it's really easy to get lost in the details of the questions, and I think to miss the big picture. Um, so let me see if I can remind you of what the big picture is. So the big picture is you have a multi-tool, if you will. Okay, the multi-tool. We talked about convergence. The convergence says yes, this multi-tool is valid to use. Okay, but the catch is that we don't know how close, like, this isn't the perfect tool for the job. The question is, how close to doing a good job will this multi-tool do? And I think, for example, of times when I've had to unscrew things with pliers. Maybe you've done that. It's like you have a little nut and you're trying to unscrew it with pliers. And sometimes they'll do the job, but they always will chew the bolt up, right? They're going to chew that thing up and it's going to get really ugly on the top because you're not really using the multi-tool in an optimal setting, right? And so this section on approximation is really asking the question of how, um, what do we have to do with those power series, with those Taylor series specifically, in order for us to have a good enough approximation of the specialty tool that we can get the job done and get the job done well. And so, whereas a power series is an infinitely long polynomial, in this section we're going to talk about truncating the power series, truncating the Taylor series, and saying if if we have just a second degree or a third degree, that'd be like a quadratic or a cubic or a quartic. If we have a short polynomial that does end, it's not infinitely long, like how good is that at approximating whatever it is that we're trying to approximate? So here we go with Taylor series and approximations. Now, the next question asks us to answer the following for f of x equals 1 over square root of x. When we're looking at the Taylor series centered at x equals 16. And this is the same question we looked at earlier. So before we go back, before we go on, I want to go back and simplify it briefly. So let's scroll back and notice that we had all of these ugly coefficients, which could be simplified. And if you know if you've been around computers a little bit, you might recognize that these are all powers of 2. So this is like 1 over 2 squared, negative 1 over 2 to the 7th power, 1 times 3 over 2 to the 12th power. We're going up by 5 each time here. Minus 1 times 3 times 5 over 2 to the 12 plus 5 would be 17th power. 1 times 3 times 5 times 7 over 2, 17 plus 5 is the 22nd power. So those are our coefficients. I've just cleaned them up a little bit because they will help us in our next example. So here we are in this next example. We want to find the Taylor polynomials T0, T1, T2, T3 centered at x equals 16. So this looks a little scary. It might even look like a bunch of Terminator movies to some of you, but this is actually pretty straightforward. So if we look at T0, T0 is simply the Taylor polynomial that just includes the very first term. So in this case, T0 will be 1 over 2 squared. So again, T0 is just the very first or the 0th term in the Taylor series. So there's your T0. So then if we look at T1, T1 will equal the first term, 1 over 2 squared. And then we have minus 1 over 2 to the 7th power divided by 1 factorial times x minus 16. And so this would be your t1 term. And notice it's t naught plus something else. Here's the 1 factorial that's built into the formula, and you have the x minus 16 that's again built into the formula. Now we can look at t2. So t2 is going to be t1, which is 1 over 2 squared minus 1 over 2 to the 7th over 1 factorial times x minus 16. And then we're going to go plus 1 over 2 to the 7th to the 12th power over 2 factorial times x minus 16 squared. Let's clean up that squared. And so you can see that T2 would be the second degree Taylor polynomial. It's not the full series, it's just the first, it's just the quadratic version of what's going on. In T3, same thing is going to happen. So we'll have T3 equals 1 over 2 squared. Maybe we could clean this up a little bit. So it'd be 1 over 2 to the 7th times 1 factorial, x minus 16, plus 1 over 2 to the 12th times 2 factorial, x minus 16 squared, plus minus 1 over 2 to the 17th times 3 factorial, x minus 16 cubed. So I think you should get the pattern here that t sub n, ooh, I forgot something. I got to come back and fix something. T sub n is the nth degree polynomial. If you've been tracking right, you realized I forgot something in my coefficients. It should be the my coefficients, the numerator should be 1, and then 1, and then 1 times 3. 1 times 3, and then, strut. Sorry, I gotta get them in the right spot. Sorry, it should be, so it's 1 for the first one, 1 for the second one, the third one is 1 times 3. The fourth one is 1 times 3 times 5. Sorry about that. I forgot these parts of the coefficients just in the copy from one part of the notes to the other. So again, Tn would be an nth degree Taylor polynomial. It's not the whole Taylor series, it's just the first few terms up to power n. So an interesting mathematical side note on how to write the product of evens or odds. You might say, why are we doing this? It's because we had that numerator. In our numerator, we were ending up with 1 times 3 times 5 times 7 times 9 times et cetera, et cetera. So you might be like, how do I write that? It's sort of like a factorial, but it's only the odd terms. So here's a couple of little examples. Notice if we have a whole bunch of evens here, 12 times 10 times 8 times 6 times 4 times 2, each of those terms has a power or a factor of 2 in it. So this is like 12 is 2 times 6, 10 is 2 times 5, 8 is 2 times 4, 6 is 2 times 3, 4 is 2 times 2, 2 is 2 times 1. And so if you add these up, this would be 1, 2, 3, 4, 5, 6 powers of 2, or 2 to the 6th. And 6 times 5 times 4 times 3 times 2 times 1, or 6 factorial. So that's how you could write kind of an even double factorial out. If you wanted to do the same thing with the odds, we got to play a little game. So we can take the odds, the 9, 7, 5, 3, and 1, and we recognize that that's sort of like 9 factorial, but there's a whole bunch of extra terms. So it's math. If you want something, you can have it. So we insert all the missing terms, but in order to insert them, we have to also divide by 8 times 6 times 4 times 2. So the numerator up top is now conveniently just 9 factorial. And we earlier showed how to write out kind of this double factorial with all even numbers. So that would be 2 to the 4th times the 4 factorial after you factor out the 2 out of each of the numbers. So that's kind of a quick way of writing things succinctly. Quick being in quotes. Part B. Use T0, T1, T2, T3 to approximate 1 over the square root of 16.8 and 1 over the square root of 22. Then compare these approximations to the calculator value and list the errors. Note that the absolute error is the difference between function value and the value the Taylor polynomial provides us. So I took the liberty of typing these functions into the calculator kind of on my own time. So let me share those with you. So here is our T0. Here's T1, and you'll notice that what T1 is it's Y1. So this would be like T0 minus, and then I took the liberty of writing things a little bit more simply just for the sake of clarity. And then here's T2 in Y3, and notice it references T1 and then just adds on another term. And T3 references T2 and then just subtracts another term. So I have found my I've entered my t's into the calculator, and then I can go over to my table, and I've let my x be 16.8 and 22. Those are the two values I care about, and this tells me here's the T0 approximations for both. Here's T0, here's T1, here's T2, and here's T3. And just by way of reference, we're trying to compare. Notice that 1 divided by the square root of 16.8 is, this top one would be like 0.24398. 24398, etc., etc. And the second one to 5 places would be 0. So this is 1 over the square root of 16.8. And let me switch colors. And then here, 1 over square root of 22 will be 0.2132. 2132, and it's actually 2320. And you'll notice if you look at the approximations that the top ones look pretty good, pretty fast. The bottom ones don't look, they still look pretty good, but they're not quite as good as before. So let's go back to the notes and see if we can fill all this stuff in like we were asked to. All right, so we want to look at T0, T1, T2, and T3. and we want to ask, we want to ask what happens when we look at 1 over the square root of 16.8. Okay. And so that would give me 0.25 even. And then the next one over to 4 decimal places would be 0.2437 or 38. And the next one over would be, next one over would be 0.24 2440. And the next one over would be also 0.2440, just rounding to 4 decimal places. And by way of reference, we have that to 4 decimal places, this is equal to 0.2440 using the calculator. So notice we matched our calculator value with our T2 approximation, which is pretty cool. A quadratic was good enough to give us a pretty good approximation of square root of 16.8. How about if we looked at 1 over the square root of 22, which is 0. To 4 decimal places, 0.2132. So T naught in this case is going to again be 0.25, because remember, it's just a quarter, it's a constant function. And then T1 would be 0.2031. And then T2 would be 0.2163. And T3 be 0.2122. So if you compare that to the actual value calculator gives to 4 decimal places, you can see that the cubic is close, but it's still not quite there. It looks like maybe one more term and we would have a pretty good approximation of 1 over the square root of 22. So let's think about the error. We look at the error. So the error is going to be the difference, and what we care about is the error in absolute value. So if we look at the 1 over square root 16.8 error, this is going to be, it'd be like how do I want to say this? It'd be like 1 over the square root of 16.8 minus 0.25, but I want it in absolute value. So my error would be 0.006. And then if I did this at 0.2438, my error would be 0.000175, or I think I'll just go with 2. And then if I did this at 440, my error is going to be 0.00002. And I think the same thing's below. Actually, it would be less if we had more decimal places. But you can see that there's a pretty small error if we match the column of the approximate values we ask, what is the difference between the actual and the initial? Maybe you're not seeing it. So error is equal to the absolute value of the actual minus the approximation. Because of the absolute value, it doesn't matter which one comes first. So now we could do the same thing, but with the 1 over square root of 22 error. So I have 1 over square root of 22. And if I subtract 0.25, I get that my initial error is 0.0368. Again, this is absolute value, so I'm not worried about the sign. 0.2031. The second one, I have error of 0.0101. Next one, 2163. 0.0031. So notice the error is getting smaller each time. 0.0010. So this is our error from the 1 over square root of 22. Okay, so we have found the calculator values. Just to be clear, we found our calculator values. That's in these first two columns. And then we found our errors, list our errors. That's in our second two columns. So it's our second two columns. And I simply want to point something out to try to make a connection between what we're doing here and what's happened elsewhere. What I want to point out is that there's bigger error. So this was a Taylor series. Taylor series or Taylor polynomials centered at x equals 16. So then we looked at two different specific x values. So we looked at 1 over the square root of 16.8. This would be like saying x equals 16.8. And we also looked at 1 over the square root of 22. This would be like saying x equals 22. And what I want to point out is that in the case of the red one, 16.8, we're very close to the center point of x equals 16. We're close, and we have pretty small error. But then when we looked at x equals 22, here we're far from 16. Now we're almost 6 units away. And so it shouldn't surprise us that we have a larger error when we are farther from the center point of our series. So all that to say, one of the advantages of having thinking about the center of a Taylor series is that your approximations, when you use just a Taylor polynomial, part of the Taylor series, your approximations will be better when you are close to that center point. Even if it converges absolutely, sometimes if you go, it'll take a lot of terms in order to converge or be close if you're far from that center point. There's a problem. Taylor polynomials and power series allow us to generate these approximate values like we just saw. However, these are estimates. How close are the approximate values to the actual values? Well, in order to find that error, we would need to know the exact value. We used our calculator. Actually, that doesn't give an exact value. That is giving an approximation. But anyway, we would need to know the exact value. But if we knew the exact value, we wouldn't need an estimate in the first place. So to figure out how good our approximation is, you need the actual value. Why are you looking for an estimate if you have the actual value? There's something really weird about this. We need a way to find the error that does not require that we know the exact value. Or to be more precise, we need a way to bound the error. So we need to find the error that does not require that we know the exact value. We need to bound the error and say the error is at most such and such. In engineering, I think sometimes this is called tolerance. Like we have a tolerance of up to this amount. We can this much leeway, if you will. In order to find this, we're going to need to build up a little bit more notation. So this next definition helps me understand what the remainder is in the context of a Taylor polynomial. So definition: the f have continuous derivatives up to the n+1th derivative on an open interval I containing a. For all x in I, f of x equals the nth Taylor polynomial of x plus the remainder evaluated x, where Tn is the nth degree Taylor polynomial for f centered at x equals a, and R of x is the remainder. So T is the Taylor polynomial, and R is the remainder. So to be clear, when we're doing this, we're saying that we have our f, which gives us the exact value. That's what we really want to find out. We're going to approximate it with some t, but we know that our approximation is off by some amount, is off by some error margin, which we call the remainder, or the error. So let's look back at our example 2 and try to understand this definition. So example 2 revisited. Find R3, the remainder, for the third degree Taylor polynomial of f of x equal to 1 over square root of x, centered at x equals 16. So let's start by writing out the Taylor series, maybe the Taylor polynomial. And I'm going to write it with some, I'm going to keep simplifying my notation to save ourselves a little bit of writing. So we're saying that 1 over the square root of x is equal to 1 over 2 squared minus 1 over 2 to the 7th times 1 factorial. 1 factorial. And then we also have a x minus 16 plus 1 times 3 over 2 to the 12th times 2 factorial times x minus 16 squared minus 1 times 3 times 5 over 2 to the 17th times 3 factorial x minus 16 raised to the third power. And this is our third degree polynomial, but we could keep going, right? We could say plus, the next one would be 1 times 3 times 5 times 7 over 2 to the 22nd times 4 factorial times x minus 16 to the 4th minus dot, 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 dot. So each time you can see those numerators are kind of that odd double factorial. You have a 2 to some power times a factorial, and then x minus whatever, x minus 16 raised to whatever power. Okay, so this part on the front end, there, that is our T3. And so the part on the back end goes forever, that must be our R3. So if we want to find R3, we can now see it. R3 of x will equal, the first term is going to be 1 times 3 times 5 times 7 over 2 to the 22nd power times 4 factorial times x minus 16 to the 4th power. And then we could just catch the pattern. So the next one part would be 1 times 3 times 5 times 7 times 9 over 2 to the 27th power times 5 factorial times x minus 16 to the 5th. And then it would go plus, you want one more term, it'd be like 1 times 3 times 5 times 7 times 9 times 11 all over 2 to the 32nd power times 6 factorial times x minus 16 to the 6th. And then it's going to keep going forever and ever. This one has a dot, dot, dot. So notice that the Taylor polynomial, here, T3, it ends, like it stops at the 3rd degree thing. But the other term, I don't know what color it is, the R of 3, maybe it's blue, it's going to go on forever and ever, right? Here's your R of 3, and notice there's this dot, 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 dot that just goes on forever and ever. It keeps going and going and going like the Energizer Bunny. So the Taylor polynomial, that's just the chunk of the Taylor series, truncates, it ends. The remainder is everything else. So notice that finding R of 3, this is the remainder, or you might call it the error. So it requires knowing, like to actually figure out a number for R of 3 requires either evaluating an infinite sum, that's one option, that's difficult, or it requires knowing an exact value, in this case an exact value of 1 over square root of x. And in this case, we can actually use our calculator to evaluate 1 over square root of x and get some sort of a value that at least is good to 13 decimal places. But what if we didn't have the ability? What if we didn't know the exact value? How would we be able to say something about the remainder, about the error in that case? The remainder estimation theorem. Suppose there exists a number, big M, such that the absolute value of the n+1th derivative of f of x is less than or equal to big M for all x in the interval a minus c to a plus c. The remainder of the nth degree Taylor polynomial for f centered at a satisfies the absolute value of Rn of x is less than or equal to big M times the absolute value of x minus a all raised to the n+1th over n+1 factorial. Whew, that's a mouthful. Let me just make one note about this definition, actually maybe 2 notes before we continue on with it. So the first one has to do with this interval from a minus c to a plus c. So if you picture a number line here, the x, and here is an a, then you could go a plus c would be over here on the right, and a minus c would be there on the left. And so all we're saying is that we're on an interval of where kind of like the radius of, sort of like a radius of convergence, but not quite, but an interval where that's centered at A and goes C to the right and C to the left. The second thing is that this inequality up here, where you have the absolute value of the n+1th derivative of f of x, all less than or equal to m, gives you the m part of the formula below. So we're going to use the n+1th derivative to find the m. You're always going to have the second part of the formula, which is the absolute value of x minus a raised to the n+1 over n+1 factorial. Example 2 revisited again. So we want to bound the error in T3 on the interval 9 less than or equal to x less than or equal to 22. And we want to find the upper bound, that is the max error in our estimates for 1 over the square root of 16.8 and 1 over the square root of 22. So let's see what's going on here. So 9 to 22. This is x. So we're going from 9 to 22. I think this is a typo. This is supposed to be a 23. I'm sorry. 23. So halfway between 9 and 23 would be 16. So there's our series centered at 16. And so we went 16 plus 7 and 16 minus 7. So that's this region here. And we want to find the upper bound or the max error in our estimates. So we need to find our big M. And notice in this case, we were told that we're working with T3. So the first thing we were going to do is we're going to think about our interval. We already did that. The second thing we're going to do is we're going to find our big M. Okay, so we know that we know that our n+1th derivative, of f has to be less than or equal to big M on the given interval 9 to 23. Okay, and so this will help us find that big M. So how are we going to do that? Well, in our case, the n is going to be 3. So we need the fourth derivative of f, and we've already taken our fourth derivative. Our fourth derivative of f will be, oh my gosh, let's see. So this would be, I think I've got 1, pardon me, I'm losing it. I gotta think. So it's my scratch work. So we had x to the -1/2. That was our original function. Our first derivative was -1/2. X to the -3/2. That was our first derivative. Then we had our second derivative, x to the 5/2. So this is our original function, f prime, f double prime, f triple prime would be, looks like the 3 times 5 over 4, x to the -7/2, and the fourth derivative will be -3 times 5 times 7 over 8, x to the -9/2. Okay, so we know that the fourth derivative of x is going to be, what did we just say? -3 times 5 times 7, x to the -9/2 over 8. Okay. So what are we going to do with that? And we're looking at the absolute value of this thing. And let's see if we can rewrite this. So this thing will be less than or equal to m. So this would be like, the absolute value doesn't matter. So this would be 3 times 5 is 15, times 7 is 105. So I have like
105 divided by 8 x to the 9 halves, all in absolute value, is less than or equal to m. And we're on the interval 9 to 23. Okay, so notice that your x values are in the denominator. And so the bigger your x values are, the bigger that denominator is, and so the smaller the overall quantity is going to be. And so this is going to be greatest, in this case, because the function is decreasing, this is going to be greatest when x is smallest on the interval, that is when x equals 9. Okay, so we want to be the greatest because we want it to be the greatest because we're looking for big M, which is going to be bigger than everything else. So this tells us that our big M, we get to choose it. So we're going to say let big M be equal to 105 divided by 8 times 9 raised to the 9 halves power, which if we found a decimal, that would be about 105 divided by 8 times 9 to the 455, or it's a pretty small number. So I've got 0.000666682. So I'm saying my fourth derivative is always smaller than or equal to this thing on the interval 9 to 23. Okay, so this is our upper bound for the fourth derivative. So we found big M. Now we're going to use it. So 3. We're going to bound our error. The remainder, aka the error. So we know from the Taylor's inequality definition that we were given that our remainder is less than or equal to big M times, and then we have absolute value of x minus a is 16, raised to the n plus 1, which would be 4, divided by n plus 1 factorial, which would be 4 factorial. And we want to evaluate this for the M value that we found. Here's our M value. And we want to also evaluate it for 2 different X values. So evaluate when X equals 16.8 and when X equals 22. So we look at these one at a time. We know that remainder, that error, is less than or equal to 0.000666682 times, if we put in the 16.8, we'll have absolute value of 16.8 minus 16, all raised to the 4th power, all divided by 4 factorial, which is equal to about, let's see if we can crunch this thing. So it'll be 0.000668682 times 0.8 to the fourth power divided by 24. So I've got that my remainder is less than or equal to 0.00000114. So what I want to point out is this is a very small number. Very small error. Let's do the same thing when x equals 22. So if we do the same thing when x equals 22, we have that the remainder, the error, aka the error, is less than or equal to same m 0.000666682, but now we have 22 minus 16 raised to the fourth power, all divided by 4 factorial, which would be equal to all that same stuff, but my 0.8 is now a 6. And so my error is 0.03, or my max error, 0.036. Okay. This is a larger max error. So let's make sure you see what's happening here. So we really have two things going on. So one thing that's happening that I want you to see is that when we estimate at 16.8, we're looking pretty close to 16, close to that center point. And when we're close to that center point, we have small error. Close to that center point, you've got small error. That's cool. When you go at 22, that's much farther from the center point, and so you'll have a large error. Close to the center, small error. Far from the center, larger error. So that's the first one thing I want to point out. The second thing I want to point out is that we now have an inequality. Remember, this is an inequality around the error. Okay, saying we know something about our error even without knowing the exact value of the function. And so this gives us a bound. It says the worst that our error could be in the first case is about 0.00001. It's a very small error, and we can know that even without knowing what 1 over the square root of 16.8 is. We're also able to determine that the max error, the worst case scenario for 1 over square root of 22 is no worse than being off by 0.036. And again, we're able to find that worst case maximum error without knowing the actual value of 1 over square root of 22. So that's why this error bounding remainder theorem is so valuable. It gives us a maximum worst case scenario for our error without requiring that we know the exact value, which is the very thing that we don't know. Otherwise, we wouldn't be doing this estimating in the first place. So practically speaking, on the calculator, you can think about the calculator evaluating the sine function. The calculator knows it only shows 13 decimal places. So it says, how many terms do I need to use in my series in order to have my max error be smaller than whatever it is to 13 decimal places. So it's like that gives you, that's part of why that precision is so important on a calculator, and also why they can break down if you kind of go to a greater degree of accuracy than they are able to track.
So example 8.4. Determine the number of terms of the Maclaurin series for e to the x that should be used to estimate e to the 0.1 to within 0.00001. This question is different than the previous example. In the previous example, we were trying to figure out, we were trying to use the remainder estimation theorem to give us a bound for our error. So it's like we knew the value that we had, we wanted to find the error using the remainder estimation theorem. This question sort of works in reverse. Here, we know the amount of error. In engineering, we might call that the tolerance. So we have the error or the tolerance that we can accept, and we're going to use the remainder estimation theorem to try to figure out how many terms are required in order to be within that error or within that tolerance. So in order to work through this question, we're going to have to review that remainder estimation theorem from the previous page. So recall, here's our theorem. I'm just going to copy paste it. So recall, so here's our remainder estimation theorem. Okay, let's see if we can understand what it does. So the remainder estimation theorem says that suppose there's a number big M such that the magnitude of the n+1th derivative of x is less than or equal to big M for all x on some interval, then the remainder of the nth derivative of the Taylor polynomial for f centered at a satisfies this inequality, that the magnitude of the remainder is less than or equal to big M times the magnitude of x minus a all raised to the n+1 over n+1 factorial. So let's see if we can try to figure out what here is known and what here is unknown in our context. So in our case, we're going to be looking at a Maclaurin series. So since we're talking about a Maclaurin series, that says we're looking at things that are centered at A, and specifically that tells us that our A is going to equal 0. Okay, so that's not too bad. Okay, we also know that something about those n+1th derivatives. So here there's a whole bunch of stuff about n+1th derivatives. Our function that we're working with is e to the x, and so it should be clear that the n+1th derivative of e to the x will always be e to the x. Furthermore, we know that we care about the absolute value. There's like an absolute value here, and so it'd be an absolute value around the n+1th derivative, but we know that e to the x is always positive, and so we can disregard that particular absolute value. So what does that tell us? Together, these things tell us that, see if I can clean up my work here. These things tell us that e to the x is always going to be less than or equal to some big M, and that's going to be on the closed interval from a minus c to a plus c, but we remember that a is equal to 0. So this will be from negative c to c. Okay. We also know that the a in this formula is going to be 0 because it's the same a. And we also know that the x that we care about, we're looking for the remainder at a specific point. Ooh, I've already used green, pardon me. We care about the x at a specific point, and the specific point that we care about is the x being 0.1. So what we're saying here, if we could try to translate a whole bunch of these things is we're saying that that the remainder, the absolute value of Rn of 0.1 is less than or equal to some big M times, remember x is 0.1 minus 0, so that's going to be positive. So I have 0.1 to the n plus 1th power divided by n plus 1 factorial. Let's see if we can continue to build on this. So we know that this remainder over here on the left side is the smallest thing, and lest you forget that that remainder, that is our error. And so what we're trying to do is we're trying to bound that error, and we're trying to force that error to be under some value. So in order to do that, we're going to try to pick some, we're going to try to find the n that makes this error be under the given amount. So we want, right here, we want this less than, and here's the magic number, we want it less than the 0.00001 that we're given. So we want our error to be less than 0.00001. Okay. So in order to do this, we're going to force our quantity over here on the right side to be less than or equal to that 0.0001. Okay. So what are we trying to do? We need to solve for where m times maybe 0.1 would be a tenth. So this would be like 1 over 10 to the n plus 1 times n plus 1 factorial less than or equal to 0. Ooh, I lost a 0. 0.00001. You'll notice that in this inequality, there are two unknowns, m and n. So there's two unknowns, that's too many. And so in order to take care of that, we must, ooh, sorry, my stuff's bouncing around on me. So here there's two unknowns. N and m. And so in order to take care of that, we're going to take advantage of this previous statement where we had that e to the x is less than or equal to big M on negative c to c. And so we get to pick our c. So we pick c. And basically, the c that we want to pick, it must include, so that negative c is less than or equal to 0.1. That's the number that we're given, and less than or equal to positive c. So here's the 0.1. So we're going to pick the c so that 0.1 is in that region. And then we're going to also pick it in such a way that it's that gives us a value that we know. Such that we know e to the c
without a calculator. So let's draw a picture here. So here's X and Y. Here's Y equals e to the X. And we know we cross at 1. And here's the 0.1 that we care about. That's that blue number. And then we want to pick a C that's some number, so that our C, need more colors. So these C's are going to go from they're going to be symmetric around 0. So it's going to be some value here, negative C, some value over here, positive C. Okay. And we want to know the Y value up here at e to the C. So we want it to the right of 0.1. We want it to be something that's known, something that's easy to work with. There's lots of options, but a number, like if we let C equal 1, then the number that would come out would be like e to the 1 or e, which is a number that we know, but we kind of got to use our calculator a little bit too early. So maybe I'm going to choose, again, this is a choice. So I'm going to choose C equal to the ln of 2. And the reason I'm going to choose C equals the ln of 2 is because since I know e to the ln of 2 equals 2. So it's a nice, clean, friendly value. So let's see if we can back up and see what we've done. So we want to have this e to the x less than or equal to big M on negative C to C. And so I know that the highest value that e to the x takes on the interval from negative ln of 2 to ln of 2 is the number 2. So let's just see if I can put all that stuff together. What are we saying? That is e to the x is always less than or equal to 2 when negative ln of 2 is less than or equal to x is less than or equal to positive ln of 2. So here's the yellow ln of 2s, the plus and minus C. And so this 2 right here, this is a really important number 2. This is going to be my M. So we can from there take advantage, we can go back to that red inequality that we're trying to solve. And we can say that that means we're trying to solve 2 over 10 to the n plus 1 times n plus 1 factorial. And we want it to be less than or equal to 0.00001. Let's see if we can figure out how all this stuff will work. So if we, probably the easiest way of doing this would be to choose different values of n. So if n equaled 1, then this would be like 2 over 100, because it'd be n squared, times 1 plus 1 or 2 factorial, less than or equal to 0.00001. So that would be 2 over 2, those would be canceled, so it would be 1 over 100 or 0.001 less than or equal to 0.00001. This is false. So what that tells us is try a higher value of n. So if n equals 2, we're going to get 2 over 10 to the 2 plus 1, or 10 to the third. So I've got 1,000. And then 3 factorial, which would be 6. Maybe I'll just write it as 3 factorial. Less than or equal to 0.00001. And you could see this is over on the right side, this is a 10th, 100,000th, 10,000, 100,000th. So you got 100,000th on the right, and on the left, you've got 1 over 3,000. So again, this is going to be false. Okay. If n equals 3, we get 2 over 10,000 times 4 factorial, 24, less than or equal to 0.00001. And I think that one is true, but I feel like I better check with a calculator. So this thing here on the left is 0.023458 repeating. And that is indeed less than or equal to 0.0000001. So it's true. So let's backtrack. I think it's probably pretty easy to forget what this is saying. So the question says, determine the number of terms of the Maclaurin series that should be used to estimate e to the 0.1 to within 0.00001. And so what we have determined is that we need to use 3 terms. So conclusion. So if we used n equals 3, so if we took, we're saying that e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus da 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 da. We're saying that if we chop this thing off with n equals 3, we go, here's n equals 0, 1, 2, 3. So if I took all of this stuff and I chopped it out, so we're saying e to the x is equal to 1 plus x squared over 2 plus x cubed over 3 factorial. And this is now approximately, right? Within 0.00001 of the actual value. When x equals 0.1. So what do we say? And just make sure it's clear. So our answer was 3 terms. 3 terms with, that is 3 terms with a 3rd degree polynomial. So I'm not counting the constant term. We could also check this just to double check. So we could check. There's our conclusion. If we wanted to check, we could compare. So if we compared e to the 0.1 on a calculator, so if I did e to the 0.1 on a calculator, I get something like 1.10517091808. And if I compare with the approximation, which would be 1 plus 0.1 plus 0.1 squared over 2 plus 0.1 cubed over 6, which is, let's see if I can put that into a calculator as well, which is 1.1051666, repeating. And so notice they match on the first term, they match on the second term, they match on the third term, they match on the fourth term, they match there. And then you have a 7, and then here you have 6, 6. So they are indeed within 0.00001. They're the same to the 5th decimal place, which is pretty remarkable. Let me zoom back camera, and so you can see that final conclusion. So here's the initial page, and then here is the follow-up. So there you have an example of how we would use the remainder estimation theorem to determine the number of terms of the Maclaurin series for e to the x that should be used to estimate e to the 0.1 to within 0.00001 of the actual answer.
Oh my gosh. So there you have it. Taylor series and approximations. Definitely one of my favorite topics. There's so much nuance in it, so much coolness. But again, it's really easy to get lost in the weeds. Remember, the big picture is you have this infinitely long polynomial. We want to truncate it, take just a few terms, and ask, how do we know that those terms are going to do a good job of approximating what we used to do with an infinitely long polynomial? You ask, why would we want to truncate? Well, we want to truncate because most computers, your cell phone, your text and friend graphing calculator, all of these kinds of tools, well, those kinds of tools are really good at doing things that have a finite list, and they're really bad at doing things an infinite number of times, right? When you try to do something an infinite number of times, that gives you what's called an infinite loop. And so we don't want to have in practice, whether we're doing it by hand or with our text and friend, we don't want to have to do something an infinite number of times. We want to truncate, stop after 2, 3, 4, 5, 6, 10, 20 terms. But we want to make sure that we know that when we're truncating, we're still gathering the most important information, and that we're not going to miss the moon with our rocket, or have our bridge collapse, or have our computer fall apart, or whatever. So there you have it, approximating with Taylor series.